Hi, in the 7th part I treat the arithmetic subtraction commands. At the beginning of this video I explain how the binary subtraction works. You don't need to understand it because CPU does work for you, but it doesn't hurt either. Let's take an 8-bit binary number minus another one. We have to start with the least significant bit. So 1 minus 1 is 0. 0 minus 0 is 0. 1 minus 0 is 1. 0 minus 1 does not work. It's the same as in the decimal system, except for the value. In the decimal system you borrow 10, but in binary you borrow only 2, because it's base 2 and not base 10. So 2 minus 1 is 1. 0 minus 0 is 0. And here we have to borrow from the left again. So 2 minus 1 is 1. 1 minus 0 is 1. And the last one, 0 minus 0, is 0. Let's do the counter check in the decimal system. So 149 minus 41 equals 108. That's correct. Let's do another example. 1 minus 3. So 1 minus 1 is 0. And now we have a problem. There are only zeros. We have to borrow not from the far west, but the far, far left. Two minus 1 is 1, and the rest, 1 minus 0, is 1. There's an infinite number of ones, but for 8-bit CPUs we consider only 8 bits. If you have a calculator where you can work with binary numbers, it will probably show you many ones. So let's do the counter check in the decimal system. 1 minus 3 is minus 2, but if you look at the number 1111110, that's 254. That doesn't look like minus 2. So as I explained to you in previous chapter, the most significant bit, that's a bit on the left side, this one. It indicates if the number could be a negative number, 0 is a positive, and 1 represents a negative one. However, this interpretation is up to the programmer. If he wants to represent an unsigned byte, that is 0 until 255, or a signed byte, that's 0 until 127, and minus 1 until minus 128. If you want to define it as a negative number and want to know which negative value it represents, you have to subtract it from 256. 256 because there are 8 bits and 2 to the power of 8 equals 256. If you take the difference, that's 2. So this number represents plus 254 or minus 2. The easiest way to do the conversion in binary is to do the complement. Complement means 1 is inverted, will be 0, and 0 will be 1. And to that complement you just add 1. 1 and 1 is 1, 0. So you have your 2, your minus 2. Let's do another example. This number represents 213 of minus 43. You do the complement, add 1 to it, do the math. That's 43. Or in this case, minus 43. If you take that number, you do the complement again and add 1 to it. It should represent the same number. That's how it's done in binary. Okay, let's try this in the simulator. Here we are in the Intel 8085 simulator. Let's load the accumulator with 1 and do a subtraction. SUI means subtract immediate. So in this example 1. Then we subtract 2 from it. Load, for example, register D with the value 3 and subtract D from A. Let's do a complement of the accumulator and add 1 to it. Do a complement of the accumulator and add 1 again to it. So, let's have a check. Accumulator is loaded with 1, subtract 1 from the accumulator, equals 0. Sign flag is 0, there's a positive number. 0 flag is 1 because the accumulator is 0. And the parity is 1 because there are even numbers of 1. 0. 0 is even. Carry flag is not set. Let's subtract 2 from it. Equals FE. The sign flag is set because it could represent a negative number. 0 flag is 0 again because it's not 0. The accumulator is not 0. The parity flag is 0 because if we check the number FE, there are 1, 2, 3, 4, 5, 6, 7 ones. That's not an even number. That's why the parity flag is 0. And the carry flag is 1 because we changed, there's an overflow from a positive number to a negative number. And the next command, loading the register D with 3 and subtract it from A, that's FB. And we're doing the complement of the accumulator and add 1 to it, so the number is minus 5. If we do the complement again, adding 1 to it, we will receive FB again. So next to the subT command, you could also write sub A, B, C, D, E, H, L and memory register M. How do you subtract from a 16-bit value? So if you want to skip the byte by byte part and jump directly to the 16-bit command, as in the 16-bit addition video, I have to disappoint you. There's no such command on the Z8085. You have two possibilities now. Continue to watch or switch to the Z80 CPU. Okay, let's do an example here. Load two 16-bit values. So we have to subtract 3, 4 from 7, 8 and 1, 2 from 5, 6. We can only do it in the accumulator. So we have to load the accumulator with L, subtract E from it, loading back the value to L, loading accumulator with H, subtract D from it and moving it back to H. So A is loaded, subtract E from it, so A minus 4 is 4 and 7 minus 3 is 4. Put in 1, 2, 3, putting it back to L, and subtracting D from 56. 7 minus 2 is 4. 5 minus 1 is also 4, 4. Putting it back to H, and that's it. Let's do a quick check in the calculator. 5, 6, 7, 8, minus 1, 2, 3, 4. That's 4, 4, 4. So in this example we had no subtraction with a carry flag. Let's do one. F4. So 8 minus 4 is 4, but 7 minus F, there will be a carry flag set. See, the carry flag is still set and the result will be wrong. Because here 6 minus 2 is 4 and 5 minus 1 will be 4. That's wrong, because we don't consider the carry flag here. Let's do a quick check on the calculator. 5, 6, 7, 8 minus 1, 2, F4. So the result should be 4, 3, 8, 4. So we have to change this subcommand with the command sub with borrow. Sub with borrow will consider the carry flag. Carry flag is set, and the sub is borrow. So 6 minus 2 is 4, minus 1 is 3, and 5 minus 1 is 4. 4, 3. So the result is 4, 3, 8, 4, which is correct. If you want to see the same examples in the Z80 simulator, stay tuned. Otherwise, see you in the next video. Bye bye. Welcome to the Z80 simulator. Let's do the same example. Loading the accumulator with 1. Subtract 1 from it, subtract 2 from it, loading the D register with 3, subtract D from it, and do a complement from the accumulator and adding 1 to it. So one is loaded, the flags are not changed. Subtracted 1 from it, sign flag is 0 because it's still a positive number. 0 flag is 1 because the accumulator is 0. And the parity flag is not like the Intel 8085. You can watch the explanation of the video, don't remember, I think it was the first edition video where I explained the flags. And the carry flag is not set. So next step, -2. Sign flag is 1 because it's a negative number, and the carry flag is set because there was an overflow. D is loaded with 3, subtracting from FE, and that's FP. To know the negative value of the number, we do a complement and adding 1 to it. That's 5. In the Z80, there's an easier way to do it. Just command this out, and there's the command negate. If you do another negate, so do the example again. That's the result, FP. We do a negation, that's 5. Negate again, that's FP. Maybe you have remarked that I didn't specify the accumulator here, because there is no simple subcommand with 16-bit numbers. There is one with a subcarry, but not a simple subcommand. So if you specify A here, he won't recognize it. So for sub T, there's also sub A, B, C, D, E, H, L, and the memory access, and IX plus an index, and also IY plus an index. Let's do a 16-bit subtraction example. So loading register DE is 1, 2, 3, 4. HL is loaded, DE is loaded, so we are going to subtract DE from HL. If you want to be compatible with the Intel 8080 or 8085 code, you have to do the subtraction command in the accumulator. So loading L to A, subtract E from it, then putting A back to L, loading H to A, and subtract D from it and putting A back to H. So let's do it. Loading accumulator with L, subtract E from it, loading accumulator back to L, loading H, subtracting D, so L is loaded to A, subtract e from it. So 8 minus 4 is 4. 7 minus 3 is 4. 4, 4. And the carry flag is not set. Putting a back to L. Then loading h to a. And 6 minus 2 is 4. And 5 minus 1 is also 4. 4, 4. Putting the result back to h. Let's do a quick check in the calculator. 5, 6, 7, 8, hexadecimal, minus 1, 2, 3, 4, equals 4, 4, 4, 4. Let me change the value here. So 8 minus 4 is 4, and 7 minus f, there will be a carry. So the carry flag is set, but with the next sub command we won't consider the carry, so the result will be wrong. Five, 6, 7, 8, minus 1, 2, f, 4. The result should be 4, 3, 8, 4. So here we can't use just the sub command, but we have to use the sub with carry command. And here you have to specify a, comma, d. So carry flag is set, and here we are using the sub with carry command. So 5, 6 is 6, minus carry flag is 5, and 5 minus 2 is 3. So 4, 3, and the result is now correct, 4, 3, 8, 4. There's an easier way to do it in the Z80 CPU. You have the sub with carry, HL. The E, there's a sub with carry, HL. BC, there's also a sub command, HL, comma, HL, and there's a sub command, HL, comma, stack pointer. But we will use here only the first one. This problem with the sub with carry command, you have to be sure that for the first command the carry flag is 0. There's no carry clear flag command, but there's a complement carry flag. So you have to first set carry flag, set carry flag, complement carry flag. So HL and E is loaded, setting the carry flag is set, complementing the carry flag is 0, and now doing the subtraction. And the result is 4, 3, 8, 4. That's all for the subtraction commands. I hope you enjoyed the video, and see you in the next part. Bye bye.